MOSFET we are done, and I have already told you that even for the P channel DMOS, for the P channel DMOSFET also it is same. It will be the same. Just in the we are going to replace P by N, N by P, all those things. Okay, so before going on to the E MOSFET, we have to study the drain characteristics and transfer characteristics. So the drain and transfer characteristics of the N-channel MOSFET, it looks almost same as the JFET, the characteristics only. So let us see how it looks. So this ID, and again here also we are going to plot across VGS. So in N channel MOSFET, what kind of gate to source voltage we are going to give in I'm talking about the transfer characteristics.
Negative, sir.
Negative will be giving. So that means it will be minus VGS. Now again, when the VGS is 0, the drain current will be maximum. And again, as we have seen, when we keep on increasing this VGS value, the current will also keep on decreasing. And finally, it will reach to a point, and that point we call it as a pinch of point or pinch of voltage. So it is the voltage where the current becomes 0. Okay, the drain current becomes 0. But unlike our JFET, we have one more characteristic here. In JFET, we were just controlling the flow by increasing or decreasing the depletion layer. But is by giving a positive voltage, was there any chance of increasing the drain current there? Listen to my question. In JFET, there we were using the PN junction or the gate voltage to increase or decrease the depletion region such that the current can increase or decrease. But the current can increase to the maximum extent of ID. That is maximum 8 milliampere or something. It was increasing. Okay. Were there any chance, suppose if I am going to forward bias that, were there any chance to increase the drain current beyond 8 milliamperes there? Any chance of additionally increasing the drain current? Additionally increasing the drain current? Okay. Now, in MOSFET, is there any chance of additionally increasing the drain current? While explaining the operation yesterday, I told you what will happen when gate voltage is positive, what will happen when the gate voltage is negative. Is there any chance of increasing this ID above this 8 milliampere, or because we assume that ID 8 milliampere is a maximum, but is there any chance of increasing this current? Kirtana?
Yes, sir.
Is there any chance of increasing beyond this 8 milliampere?
Sir, amplifier.
No amplifier. I'm just talking about normal, simple. I'll take a transistor and I'm going to increase.
Sir, if we reduce the VGS, I think we can increase, sir.
Reduce the VGS means to what extent?
Uh, so, for example, if it is at minus 4 volts, we have to reduce to minus 2, like that.
Okay, it will be increasing, 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 and it will come to this point. I'm asking now, is there any chance of increasing like this beyond this limit?
Don't know, sir.
Hmm?
Don't know, sir.
No, sir. Because if we give positive voltage, the
Hmm.
electrons will
Hmm.
uh, um, the electrons will get repelled, sir, from the region.
If you give positive voltage, electrons will repel.
Like they'll move away, sir.
See, this is our gate. This is N well, this is N well. Between this, we are having N channel. This is the P substrate. So this is in connection. This is not in connection. This is drain. This is source. What I'm telling is, if this gate voltage is made positive, what kind of electric field is created here? Positive electric field. And this P layer, whatever we are taking now, this P substrate is of majority charge carriers. It contains as holes. What about minority charge carriers? Electrons. If a positive electric field is created across this area, what happens to those electrons which are present here?
They will move towards it, sir. They'll get attracted.
They will get attracted and they'll get added on to this. See, yesterday I was giving an example. There are 100 people who are moving in a rally, and there are some people who are standing beside the road, and they get attracted by that, and they also join. Actually, the count was 100, but because these guys joined in the mid of the road, so now the count got increased to 104. So now this plus 4 is an add-on or it's a reduction? It's an add-on number, right? Here also, the electrons which were considered to move from this well to this well were simply moving on, and there was no expectation that these electrons will jump. But when you are going to supply positive voltage, gate voltage, during that time a positive electric field is created. Because of the positive electric field, the electrons which are minority charge carriers in the P substrate, they get attracted and they jump into this N channel. Now already some electrons are flowing and that electron has reached this level, but when you are going to make VGS as positive, instead, see, when VGS is 0, you are getting this level. Suppose if I make VGS as plus 1 volt, then what happens? Extra electron starts getting added up. So now what happens? The current starts increasing beyond 8 milliampere. This level or this mode is known as enhancement mode. Okay, this mode is known as enhancement mode. So we can enhance the current beyond the maximum level, and that enhanced current will be known as IDSS. Okay, drain saturation current. So extra current beyond 8 milli, it might go to 9 milli, 10 milli. Why it happened? Because we made VGS as positive. That's why. So there is a chance to increase the current beyond its maximum level. That is the specialty of this MOSFET. Any doubt in this? At least now can anyone tell why actually we get this enhancement mode?
Can you repeat, sir, the last few lines?
Say we were making the gate to source voltage as negative to control the flow of electrons from source to drain. So when I was making gate voltage as negative, the electrons were rippling to the N layer or N substrate, P substrate. So that number of electrons moving from source to drain was controlled. Okay, so more the gate to source voltage I'm applying, this gate voltage, negative voltage I'm applying, more electrons will get repelled from this path. Okay, so when they are going to repel from this path, less electrons will reach the drain. So the current will reduce. But when the gate to source voltage is towards zero or it is going towards zero, during that time, what happens? The repulsion gets reduced. Because of that, more electrons will flow from source to the drain. When you make gate to source voltage as zero, during that time there is no repulsion. So all the electrons will be attracted and they will be moving towards the drain. Because at the drain, we are applying VDS, drain to source voltage. But if you are going to make the gate to gate voltage as positive, during that time what happens? Here it is going to create a kind of positive electric field. When a positive electric field is created across the channel, what happens? The electrons which are in this P substrate, they get added up to this channel. They just join this channel. So now what happens? Already some electrons are moving, are flowing to that electron. Some more additional electrons are getting added up. Because of that, we at zero gate to source voltage, this was the maximum. But when you make it as plus 1 volt, because of this additional electrons, the current further increases. That mode is known as the enhancement mode. Okay.
Yes, sir.
So if we keep increasing VGS positively, enhancement mode will be continuously
Yes, it
made.
will be increasing. Yes, it will be increasing.
Okay.
It will be increasing until the minority charge carriers in this P substrates are going to be emptied. Minority charge carriers will be minimum only. Until they are going to be completely exhausted, the current is going to increase. After that, it will stop.
Okay, thank you, sir.
Okay. So this is about the transfer characteristics. The next one is the drain characteristics. The drain characteristics is the same. It is ID versus VDS. It is ID versus VDS and the graph looks the same like this. So this will be the ohmic region. This will be the saturation region. This is the ohmic region. So when positive, this is VGS, positive gate voltage is given maximum 0 volt, minus 1 volt, minus 2 volt. You can see that when gate voltage is towards negative, the drain current starts decreasing. Now, when the drain to source voltage is increasing, during that time the current will also starts increasing. In the ohmic region, it will be having that variation or it will increase. After that, it will be constant. It will reach the saturation region, so it will be almost constant. The current will be constant. So here in this we'll be having only two regions, ohmic region and saturation region. Cutoff region will be not having in this case because of the breakdown region will be not having, because the construction of the MOSFET is in that fashion, so it will not lead into breakdown region. So we will not worry much about the breakdown region. So you will be having ohmic region and saturation region. I have already told what is ohmic region and what is saturation region. So ohmic region is the region where we can increase or decrease the current based upon the applied voltage. Saturation region is a maximum current. After this, we are having P channel depletion type MOSFET. So that is just the replica of this. Just replace P by N, N by P. Okay, so that I'll be giving in the notes. So coming to the symbols, I told you symbols have their own meaning in this uh, in our electronics. So we have like this. This is the drain, source, gate. This is the substrate connection. So if the R, this is the drain and source, and you can see that the gate is in not not in touch with drain and source, because see, you can see there is a gap here, no, between this line and this line. This indicates that the gate is in not contact with the drain or source. Who is going to separate the drain and source from the gate?
Some metal oxide, sir.
Yes, that is SiO2 layer is going to separate. But if you remember the JFET, we were writing like this. This was the gate, this is a drain and source. So all were in contact. All were in contact. There was no separation, all were in contact. So that's why we are writing like this. But here, since the gate is having a separation, even in the construction, you can see gate is separated by an insulating layer, but drain and source are in contact through the channel. So this is the channel which is connecting the source and the drain. And the substrate connection, it comes in between this. And this substrate connection, if it is left without any connection, it will be written like this. Suppose if you are going to short this substrate connection, I told you we are going to short it with source, then it will be written like this. If it is shorted, we will be writing the symbol like this. If it is not shorted, then we are going to remove this part. So now here, this is a N-channel D MOSFET because the arrow mark is towards the gate. Just remember, if the arrow mark is towards the gate, it is N-channel. If the arrow mark is away from the gate, it is P-channel. So for P-channel, it will be like this: substrate is the drain, source, gate. So now if it is a shorted, if you are going to substrate is going to be shorted, then short like this. This is the symbol for the D MOSFET. The next kind of the MOSFET is E MOSFET. So E MOSFET. So E MOSFET means enhancement MOSFET. So in enhancement MOSFET also we are having two types: N channel E MOSFET and P channel E MOSFET. So first N channel E MOSFET. So in the N channel E MOSFET, the construction looks almost the same, but one thing you should remember: in enhancement MOSFET, we are not going to have a permanent channel. We are not going to have a permanent channel. So in N channel MOSFET, we are going to consider P substrate. To this, we are going to embed two N wells. After that, we are going to take an SiO2 layer. After that, SiO2, these are the ohmic contacts we are having, and in middle we have a gate. This is the source, this is the drain, this is the gate. So we know that it is in contact. So this is our SiO2 layer, and we will have a substrate connection here, that is the fourth terminal substrate connection we have. Can anyone tell me what is missing in this figure? What is missing in this figure?
So the N bar,
Hmm?
the N bar, so which is connecting the two N wells.
Yes. So N channel is missing. That means here there will be no N channel. Physically, while constructing only, N channel or the channel will not be constructed. So what you have to do? See, in order to conduct, we need a path. We need the path for the electrons to flow from this to this. Can anyone tell me? Just think. Can the electrons move from this well to this well through this P substrate? Through this P substrate, can the electrons move from this to this? See, the electrons cannot move from this path to this path without a channel, because this is a P substrate where we are having majority charge carriers as holes, and they are going to offer more resistance for the flow of this charges from N to this region. Even though you can try to move, but very minute amount of charges will be flowing from source to drain. So that's why what we have to do is, first we have to grow an channel here. We have to grow a channel. That growing a channel, the process of growing a channel or creating a channel by biasing is known as enhancement. So what we are going to do now is, we are going to concentrate the electrons in this particular region, and we are going to create a channel. See, I was in the last case, we are telling N channel, N channel. What are the majority charge carriers in N channel? Electrons. So when channel is made up of electrons, then for electrons it is easy to flow through that channel. But if the path is made up of full of P type material, P type, then it is not easy for the electrons to flow. That's why what you have to do, what we'll be doing is, first we are going to bias the gate voltage in such a way that all the electrons are whether the electrons are present in P substrate, are they present in P substrate or not? Are the electrons present in P substrate?
Minority carrier.
Minority carriers are present. So now the idea behind this operation or the concept is, we are going to bias this gate in such a way that all the electrons which are present here and there in the minority position, they get attracted towards this. They will be getting attracted towards this, and they are going to they are going to form a layer. See, when I'll take a layer here, and this is a p layer. Now what I'll do is I'm going to segregate all the electrons which are present in this entire p layer to this particular portion. Let's say all electrons are occupied here. Okay, so the electrons which are present in this entire p layer, all of them got segregated here. Now, to this portion, just to this portion, which is the majority charge carrier?
Electrons.
Electrons. Now, can I call this as an n layer? This portion only.
Yes, sir. It will be majority of electrons.
Electrons. Only for this layer, it is n. It becomes majority charge carriers as electron, minority charge carriers as hole. This concept is going to be applied here. Now, just tell me what kind of voltage I should apply to the gate such that all the electrons which are minority charge carriers, they get attracted and they get deposited over here.
Positive.
Positive. So we are going to connect a positive battery VGS. So now what happens here? It creates a kind of positive electric field. When it creates a positive electric field, all the electrons starts getting segregated here. They get segregated here. Because of that, what happens? Finally, they are going to form an N layer. They are going to form an N layer. Now, what I'll do? I have to attract these electrons through this. Now is it easy for the charges which are present in this N well to flow through this path? Is it easy for them to pass through this path? Because this also contains electrons. This also contains electrons. Is it easy for them to flow through this path?
Yes, sir.
Okay.
Yes, sir.
So now I have to create them. I have to drive them towards this particular destination. So now what kind of voltage I should apply here? Across the drain. Because I need to create an attractive force.
Again positive, sir.
Again positive we have to apply, and the other terminal will be, so this all this negative portions, they are going to be grounded. Okay, this is our VDS. So now when you are going to increase the VDS, more and more electrons will be keep on flowing towards the drain. So this is how the electrons start flowing from source to drain. Now this became an N layer, this became a P layer. Between P and N layer, what will be there? What will be there between P and N layer?
Depletion region, sir.
Depletion region. So a layer of depletion region will be created here, like this. Okay, this is how we are going to create a channel and we are going to conduct. Now one more question. Okay, now I'll switch off these batteries. What will happen? Now when you switch off this battery, when you remove these batteries, the channel will get destroyed. Okay, when you switch it on, the channel gets created. When you switch off, channel will be destroyed. That means there is no fixed or permanent channel in enhancement MOSFET. Okay, so now did you understand what is the difference between E MOSFET and D MOSFET?
Yes, sir.
So what is the difference?
So in E channel, in E MOSFET there is no channel, sir. But in D MOSFET there's a channel resistor.
Hmm. In D MOSFET, there is a fixed physical channel. We are creating physical channel. We are while constructing only. We are going to do. But here in this, we are not. There is no fixed channel. Here, channel will be created whenever it is biased. Again, the channel will be removed. So this is how the E MOSFET works. N channel E MOSFET. In the same way, we have P channel E MOSFET. Now, in this, after this, we are having, and that's why the name enhancement type, because we have to enhance the layer channel we have to create, and then we have to uh, conduct. That's why the name. Coming to the characteristics, the drain characteristics is same in this also. I mean, same ID versus VGS. Sorry, VDS. ID versus VDS, and same curves we have. So more, but one difference can you observe? One difference can you observe between our D MOSFET and E MOSFET drain characteristics?
Breakdown is not there.
Hmm, breakdown was not there also. That difference is
Voltage values, sir.
voltage values. That means even VDS is also positive, VGS is also positive. Both are positive. But what we did there, VGS, they were reverse. VGS positive means VDS will be negative. If VGS is negative, VDS will be positive, like that. Okay, this is the drain characteristics. But you should be careful. This is the drain characteristics. But you should be careful in transfer characteristics. The transfer characteristics is entirely different from JFET and the D MOSFET. The transfer characteristics will be having like this. This is the transfer characteristics. Now, can you just anyone think why it starts from 2 volt? Why not it from 0?
So, because the current will flow only when the channel is created.
Yes,
Will
very
happen.
good. So till 2 volt, this amount of voltage is utilized to create the channel. Once the channel is ready, then only the current starts flowing. Okay, that's why don't start from 0. If you start from 0, it's wrong. You should start from 2 volts. Okay, so after this, we are having just the symbols. We'll have a look on the symbols. So this is the gate. This is our drain. This is our source. This is the substrate. What you can understand by this symbol? See, there is dotted line. the breakage line between drain and source. This indicates there is no fixed channel which is going to connect the source and the drain. What was the symbol we had there? Like this. This was indicating a permanent fixed channel which is going to connect the drain and the source. But here we are having gaps here. Gaps indicates that the source and drain are not permanently connected. Okay, this is the symbol. This difference you should know. Purposefully in Viva, they'll ask you write the symbol for a MOSFET, E MOSFET, D MOSFET, and they'll ask you what is the meaning or what you can understand from this. Okay, this the dotted lines or this gaps indicates that source and drain are not permanently connected. They are permanent channel is not present. A temporary channel will be created. So E MOSFET has a temporary channel, but D MOSFET has a permanent channel. Okay. This is about the construction and working of the JFETs and MOSFETs. After this, the next thing we are having some more concepts which are related